Number 3. This actually kind of refers back to something in the middle of the previous page. So I'll put the previous page back up there again. Which apparently has a big blob of eraser stuck in the middle of it now, but if you overlook that, cosine theta I plus sine theta j is a unit vector, okay? And that means that its magnitude is 1. That's what unit vector means. And if you don't believe me, you take the x component and the y component and you put them in the Pythagorean theorem. And because that's how you find the magnitude of any vector, is using the Pythagorean theorem. And it's a trig identity, cosine squared plus sine squared equals 1. So the reason this is well, it's not only related to what I was talking about here, but anywhere throughout the whole course, whether it's an electric field vector, or whether it's a momentum vector, or whether it's, pick your favorite kind of vector, any vector can be thought of as its magnitude times its direction, where its direction is a unit vector. And any vector that's pointing at some angle theta would be, well, you see this vector here has a length of 1. So if you've got a force vector that's 12 newtons, 12 times this vector would be a vector that's 12 newtons long in the same direction, okay? So the magnitude times this unit vector, which would just be equal to I if it points along the x-axis, and would just be equal to j if it points along the y-axis. Magnitude times the direction is the vector. In this case here, we're talking about an electric field vector. So that's number 3. The answer to number 3 is just, it's 1. The magnitude of the vector is 1. Number 4. Guess I should have left that over there where I had it. Part A. What is the direction of the, I should probably get ready to write this stuff down. I even have the notebook opened up. It's unpleasant. It sounds like somebody's smoke detector is going off. What is the direction of the x component of the electric field there at point P? You got a 50-50 shot. It's either the right or the left. That's the only 2 ways an x component. Left, yes.
Is it okay if we just rotate it on instead?
Yeah, means the same thing. And the y component is up. Because, you know, you've got this, I've got the camera pointing the wrong way again. I need a cameraman, I think. You've got this positively charged rod, and electric fields point away from positively charged things. So that would be kind of like this, roughly. And when you take that and resolve it into components, the x is to the left and the y is up. And part C says which one is bigger, the x component or the y component. X is bigger, yes. I think this started out as a question I put on an exam that people didn't do very well on, and that's how it found its way into the notes. But maybe maybe you people are smarter than the people who were taking that test. That actually happens sometimes. So here's the rod kind of going along the x-axis. Point P is up here. And even from, if you break it into lots of little pieces, break the charged rod into lots of pieces, even the first one at the left-hand end here, if you draw an arrow that points directly away from that, well, this is if you've got 20 centimeters here and only 10 centimeters high, that's significantly less than 45 degrees, and that's the same direction that the field vector would have. As you move on to other parts of the charged object, that angle gets even smaller as you head down the rod toward the other end. So from any piece of that rod, the y component's going to be smaller and the x component's going to be bigger. And then number 5, similar question, only this time the point where we're talking about is directly above the midpoint of the rod. So what is the direction of part A? The direction of the x component is what it says. Yeah, there is no x component. This thing's going to point right straight up. If it's right in the middle of the thing, there's the rod. Because, right dead center like that, it's a symmetrical thing. The x components from one half of the rod will point in one direction. The x components from the other half of the rod will point in the other direction, and they'll cancel each other out. When you add, basically what you're doing in your head, even though it might not feel like calculus, you're integrating from one end of the rod to the other. You're saying, let's divide this rod up into lots of little pieces. What would the field of each little piece look like? And what happens when you add them all together? That's integration, okay? And the x components from the little pieces on one end of the rod are going to get canceled out by the x components from the little pieces on the other end. So sub x equals 0, and part B, the y component obviously points up because I've already drawn a picture of it. And which component is larger? Well, that's kind of a trivial question in this case. If the x component is 0 and the y component is not, that makes the y component bigger. And that takes care of number 5. Number 6, I imagine you're going to need a little more time for. Maybe I should toss out some hints right at the beginning as I think about it. It's very similar to a couple of examples that I ran through on the board the other day. But for part A, to get an expression for the charge on the small piece pictured there, you set up a proportion. We're assuming that the charge is uniformly distributed. That means charge per unit length for the whole thing equals charge per unit length for the little piece. And it tells you the length of the whole rod is about 11 centimeters. Unlike the ones I ran through with you the other day, I've filled in some specific numbers on this question. Thought maybe you'd like that better. So it tells you the length is right around 11 centimeters, and it tells you the charge on the entire rod. You divide the one by the other, that gives you the linear charge density, charge per unit length. You can get an expression for the charge of that little piece in terms of d theta if you go back and review the problem at the bottom of the previous page. Go look through your notes from the day before yesterday, and that'll, just do the same thing that was done there, and that'll take care of part A. And then actually part B, and as you go on through this is very similar to, I guess it was 6-2 on the previous page. Just a few details have been tweaked. Time to run through number 6. Time is going to be pretty tight for number 7. Anybody who feels like hanging around a little while after class and working on it, that strikes me as a perfectly fine idea. But for number 7, I do have solutions written up. I suppose for anybody who isn't here, I could just sort of hold it there like, that's not info, there we go. And they can just sort of click pause and see anything they need to see on. Actually, that needs to be back a little further. But, and of course, if you have any questions, as with anything, then talk to me about it sometime. But for number 6, part A, because the question says it's a uniformly charged object, that means the charge per unit length for the whole rod would be the same ratio as the charge per unit length for the small piece of it that's shown on the picture there. The whole rod has a charge of 3 microcoulombs and has a length of 0.11 meters. A typical little piece has a charge d2. And as I explained when I was going over problem number 2 the other day, the length of that little piece is r times d theta. That's S equals r theta from physics 131, only now it's not a finite chunk of a circle, it's an infinitesimal one. So it's a dl for length equals r times d theta instead of S equals r times theta. The radius of the circle is labeled on the picture, 7 centimeters, 0.07 of a meter. So you multiply both sides by r d theta and multiply and divide the numbers. So that's the charge on the little piece shown in the picture. Part B says, what is the electric field of that small piece shown in the picture? Well, like it says, on the previous page in the note packet, I kind of made a step-by-step procedure. Step 1 is the step, I think it was maybe I don't remember if it was step 1 or step 2, but one of them says that the field of a small point-like piece of an object is the Coulomb's law constant times dq over r squared. that's the magnitude of the field. Multiplying the magnitude by a unit vector pointing in the appropriate direction makes it a vector. That's what question number 3 at the top of the page was all about. For anything lying in the xy plane, that unit vector would be cosine theta I plus sine theta j. So magnitude times the direction gives you the electric field vector. Coulomb's law constant is just under 9 times 10 to the 9th. dq is the thing I figured out in part A. And see, we needed this to get it in terms of d theta, like I was saying to, I forget who I was saying it to. You can't have an integral like cosine theta dq. Everything has to be in terms of the same variable. It's got to be cosine theta d theta. And so that's why you needed that. The radius, once again, 0.07 of a meter. In some other problem, the radius might change. Well, the first one, number 1 in this section, the radius changed as you worked your way along from one end of the rod to the other, but not in this one. This is a chunk of a circle, and what makes it a circle is every point on the rod is the same distance from the center. So in this case, r is a constant, and we have the unit vector cosine theta I plus sine theta j. And I can clean it up a little bit by multiplying all those numbers together. And I almost forgot to write down the d theta. So that's the answer to part B. dE equals this expression. That's the field of one vanishingly small part of this very thin rod. To get the field of the entire thing from one end to the other, you have to add together the pieces of all the parts. So add together the fields of them. So the superposition principle. Add together the dE's and it adds up to the total E of the entire rod. The limits of integration would be from 0 to pi over 2. You've got, maybe I should make a little sketch. Here's the dE for the first little piece here at this end of the rod. dE points that way. And then the field of the next piece is a little bit above the x-axis. The next piece beyond that is a little bit further, and so on and so on. By the time you get to the other end of the rod, the field of that last piece points right straight up. So as you add together the fields of the rod's many little subdivisions, theta starts out at 0 and ends up at pi over 2, or 90 degrees if you'd rather call it that. 3.5 times 10 to the negative 6. Well, this is just recopying the thing above it. It's always a good idea to take constants out in front of an integral, just, get them out of the way so you're not tripping over them. Forgot my J. So you get the x component by integrating the cosine, get the y component by integrating the sine. Integral of cosine is sine. Integral of sine is negative cosine. That's slightly lower. Sine of 90 degrees is 1. Sine of 0 degrees is 0. So when you evaluate this at the upper and lower limits, 1 minus 0, this is equal to 1. For this one, the y term, cosine of 90 degrees is 0. Cosine of 0 degrees is 1. Minus cancels minus, and you've got a 1 over here also. And so, like it says after the question there, the electric field in volts per meter, per coulomb if you prefer, would be that. So number 7 probably is worth at least as much time as you worked on this one. Yeah, that looks like it's about the same length. I don't have more class time to devote to this. I'm going to start section 7 the next time we see each other. But I recommend that, this does not seem to be a trivial thing for people to pick up. I'm guessing most of you need a little more practice with this. So work on it. And when you get stuck, refer to those answers I wrote up. And don't be shy about seeing me outside of class. I just sit in my office all morning. I get so lonely and nobody ever comes to see me. And and as I said, if you want to stick around now, I'm fine with that.
Thank you so much for the
Okay.